You got it? I will start. Dear Father, we thank you for this day. Again, Lord, I thank you for these students. I just pray you be with us today. I pray for the people in Brussels that you give the church there an opportunity just to witness to the lost and to minister to the people that are hurting in Belgium. And again, Lord, we pray for justice, that you would just help the authorities to find the cowards who did these things and just to exact justice upon them, Lord. In your name I pray. Amen. I don't know if you guys have seen the news or not, but it's another big day for peaceful Islam. But okay, earlier section I spent far too long proving the alternating series test and far too little time talking about examples. I intend to rectify that with you guys. We are going to go lightning speed through the proof. All right, here we go. First of all, I need to tell you what is an alternating series. An alternating series is something like this. It's formed from positive, well, possibly, I guess they could be zero. Well, you know what? I'm not, if I got to look at the book again. Maybe I should make this positive. I tend to think that they could be zero, but whatever. The theorem that we have for alternating series assumes that they're positive. So I probably should just say positive. That's probably safer. I think that it's definitely the case that if they're positive, it's an alternating series. That much I can say for sure. So you have something formed that it basically goes plus, minus, where these b sub naughts, b sub k's are positive terms. I'm changing notation from the book a little bit. The book writes a sub naught minus a sub 1 plus a sub 2 and so forth like that. And I don't think that's good because he's been using a sub k as a generic term in the series for section 12.1, 12.2, 12.3, and 12.4. I am going to continue using a sub k for the generic kth term in the series we're studying, right? Which means I need another letter to describe the positive things we're adding or subtracting. So I'll call those b sub k. In other words, an alternating series is one where the kth term has the form minus 1 to the k times b sub k. Okay? Well, sorry about that. A couple of examples. I give us 3 examples to start with. My first example is the alternating harmonic series. The alternating harmonic series is basically formed from just putting some minuses in the harmonic series. So you go 1 minus a half, plus a third, minus a fourth, plus a fifth. In terms of formulas, all we did was we put a minus 1 to the k plus 1, and we inserted that into the p equals 1 series, right? This is the so-called alternating p equals 1 series, or you could say the alternating harmonic series. Now, did the p equals 1 series converge or diverge? Diverge. All right, so here's a picture of what's going on. So like, if you look at S1, what is S1? Well, S1 here, the first partial sum is 1, right? And then the second partial sum is what? 1 minus a half. So that's right here, right? I'll draw it in green for the purposes of our current discussion, right? There's S2. Then where's S3? Yeah, 5/6, right? So S3 would be the sum of the first 3, right? And then what is S4? Well, S4 subtracts a fourth, right? Goes back here. S5 adds a fifth to that, like this. And then we subtract a sixth, add a seventh, subtract an eighth, add a ninth, and so forth and so on. And you go dig, 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 and then that. Obviously, it converges to 0.692 natural log of 2. Clearly, right? I am, of course, being facetious. It is not clear at the moment why on earth this converges to the natural log of 2, but I'm telling you, we will soon have the technology to prove that. Okay? That's my first example. So what did we do? We changed something which was divergent to something that was convergent by just inserting some minuses. Okay, so, but you see the way I argued, right? The way I just argued that this was convergent, what test is that? It's nothing like anything we did up to this point, right? That's a radically different argument I just made than the integral test or the basic comparison or the limit comparison or the root test or the ratio test or the limit comparison test or the geometric series test or I think that's all my tests anyway. All right. Oh, P series. My next example, example 2, take the P equals 2 series, right? Put minus 1 to the k plus 1 in that as well. So then you'd be looking at like 1 minus a 4th plus a 9th minus a 16th plus a 25th, right? So what I'm arguing here is that if you look at this got to be less than pi squared over 6 because I happen to know through, as a point of mathematical trivia, that the sum k equals 1 to infinity of 1 over k squared is equal to pi squared over 6. So like next time you're on Jeopardy, you can show Alex what's what. And when he says, what's pi squared over, you're like, how would he, what would the question would be what, pi squared over 6? And the answer would be, what is the sum of these squares from 1 to infinity, Alex? Something like that. I don't know. No, it seems to me the trivia they have of Jeopardy is far less interesting. But there's this conflation between genuine intelligence and people who know lots of facts. This is a very different thing, genuine intelligence versus a person who's a compendium of facts, a person who can reason versus a person who can remember. These are very different things. The person who can reason is still useful in the age of Google. The person who's a compendium of facts has been replaced by Google and these things you call smartphones. But anyway, I digress. I don't know, what I said is, well, I'll shut up. Anyway, my point to you is that this is a sum of positive terms, right? So it's clear that this alternating P equals 2 series bounded below by 0, right? You might worry that just because I showed that that pi squared over 6 was larger than it, and that's immediately obvious, right? Because you're changing minuses to pluses, so this should be larger than whatever this is. You might worry that the series goes off to minus infinity, though, right? Intuitively, you might worry, because we're making things minus. You don't need to, actually, because it's a sum of positive things, right? Yeah, okay. I don't disagree with you. Okay. Now, what actually is this series equal to? I don't know. Okay. I might know. It's probably a thing, but I'll shut up. Ow! Don't do that. That's smarts. Ouch. All right, 3. The sum j equals 0 to infinity of minus 1 to the j over 2j plus 1. Sorry, I'm always kind of giddy after I accidentally go 10 minutes over class in the earlier section. The only thing worse that you can do is start class 10 minutes early. I did that once. Like, why is everybody late today? People kept coming in late is the weirdest thing. And then finally, after I was done lecturing, I think one of them told me, I was like, oh, you jerks, why didn't you say something? You should, if a professor starts lecturing to you 10 minutes early, you should politely interrupt them and remind them what time it is. It's not nice. Why? Well, you're a bad person. Oh, you thought, no, wait a minute, sorry. You're saying 10 bonus extra minutes of lecture, it's very exciting. Okay. I can accept that. I'll accept that. If that's your reasoning, I will accept it. J equals 0 to infinity. So this one, at j equals 0, you get 1. J equals to 2, you get minus 1 squared, which is, j equals 1, you get minus 1 over 3 factorial, which is 6. J equals 2, you get plus 1 over 5 factorial, which is 120, and so forth. All right? And if you keep going, plus dot, 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 sine of 1. Again, obviously, right? If you don't believe me, though, you can check it out. Sine of 1 minus 1, all right, is actually equal to 0.1585, and that happens to be less than 1/6. And if you take sine of 1 minus 1 plus 1/6, it's less than 120th. So in other words, the difference between sine of 1 and the first term in the series is less than 1/6. The difference between this series and the sine of 1, if I just take the first two terms in the series, if I take 1 minus 1/6, that is within 1/120th of the sine of 1. And if you believe me, I mean, you don't have to, this actually gives us a way of approximating the sine of 1 to arbitrary precision. You can get as close as you want to the decimal form of sine of 1 by just adding these fractions further and further and further down. More on that in a little bit. So I'd like to just stop and think about these examples we have so far, okay? We have 3 examples, and I want to use these 3 examples to try to explain to you guys a term. So here's the observation. There are convergent series, all right, sum of a sub k, for which the series of the absolute value of the terms, or the absolute value series, you could say, converges. And there are other ones for which the series formed by the absolute value of the given series diverge. All right, now here's the standard terminology here. If you're given a series, and the absolute, if you're given a convergent series, and if the absolute value of that series converges, then the given series, the sum a sub k, is said to converge absolutely. Or you could say it's an absolutely convergent series. These are special ones. It's not just convergent, it's absolutely convergent. That's a definition, but it's a good definition, both in terms of its role with absolute value and the fact that absolute convergence really is, it's a stronger form of convergence than just convergence. The other term is conditionally convergent. If the series converges and yet the series of absolute value of this given series diverge, then the series is said to be conditionally convergent. As I cautioned in the earlier section, this is slightly dangerous terminology. You shouldn't think the series, it was converging, right? But then it didn't converge, right? I mean, that's not the case. Given the sum a sub k, given the series with term a sub k, it either converges or diverges, all right? So this term is just another description of how it's converging. It's conditionally convergent. That by definition means the series of absolute values diverge. Now, there's only, so the first example I gave you here, this was actually a conditionally convergent series, right? Because if you look at minus 1 to the k plus 1 over k, the absolute value of this is what? It's 1 over k. What's that?
It's going to negate that.
Right, exactly. The absolute value kills the minus 1 to the power. That's an important algebraic observation, right? And so we have that the absolute value of a sub k is in fact the p equals 1 series, which diverges, right? So that makes the alternating harmonic series, in fact, the quintessential example of a conditionally convergent series. It's my go-to example of a conditionally convergent series. So the alternating harmonic series converges, but just barely. Yes, sir?
Are you going to be a stickler, if we have to write convergent or not? Do we have to write conditionally convergent? Or just when we use absolute value, we have to write absolute convergent?
Well, if I ask, oh man, I just realized I didn't state a theorem earlier section. Curses. It is true that absolute convergence implies convergence. Every absolutely convergent series is also convergent. That almost seems like a definition from what I wrote on the board, though. But what I'm saying is, if you know that the series of absolute values converge, it follows that the series converges as well.
But it's not, that's not reciprocal.
No, otherwise this wouldn't be meaningful. I'm usually, I mean, it depends on the question. I do want you to know the difference between convergent and absolutely convergent. Most often, though, I'm just asking, does it converge or diverge? And maybe, if possible, find the value of its sum. Let me go on. So case 2 and 3, those were absolutely convergent series, because in case 2, if you take the absolute value of a sub k, you get 1 over k squared. Well, that's the p equals 2 series, which we know converges, right? So it's absolutely convergent, my example 2. And example 3 is also absolutely convergent, because if you take the absolute value of this minus 1 to the j over 2j plus 1, what does that give you? Well, that gives you 1 over 2j plus 1 factorial. What did I tell you guys yesterday? If we want to analyze the convergence or divergence of something with a factorial, we should use the ratio test. Yeah. So, or at least I try anyway. It may, or I mean, there's an exception to every rule in this part of the material, okay? Not much I can say universally. I can say some very universal things about geometric series, but if I try to get carried away with advice about generic series, I will get into trouble. So I try to guard my words in here. So the absolute value of aj plus 1, I mean, I try not to lie to you. The absolute value of aj plus 1 divided by the absolute value of a sub j here, which is what I'm trying to analyze. Does this absolute value series converge or diverge, right? So check it out. That gives us this 2j plus 1 factorial divided by 2j plus 1 parentheses plus 1. What is this? This is 2j plus 3 factorial, right? Now 2j plus 3 factorial we can write as what? 2j plus 3 times 2j plus 2, and then what do I have left over? I've got 2j plus 1 times 2j times times 3 times 2 times 1. In other words, what's left over, of course, is the 2j plus 1 factorial. But that cancels with the 2j plus 1 factorial in the numerator. And it just leaves me the product of 2j plus 3 times 2j plus 2, which clearly goes to 0. 2 plus 1. I'm not just being glib. So this distribute 2 times j, and then that's 2 plus 1, so 2 plus 1, 3. Yeah. This problem's a little bit forgiving. I think there's a few algebra mistakes you can make here and still get the right answer. So anyway, if that goes to 0, then what does the ratio test say? It converges, right? Because it went to 0, which is less than 1. We're looking at a series with positive terms. Oh man, I erased it. I had something over here. So therefore, let me put the finishing blow here. Therefore, the series, absolute value of a sub j converges by ratio test lambda equals to 0, which is less than 1. Right? Hence, the sum a sub j is absolutely convergent. Try to remember tomorrow to prove that absolutely convergent implies convergent. It's not that complicated, but just so I don't get off track in the different sections, and I owe them it now. I'll owe it to you guys tomorrow just to be everything equal. All right. You guys are Bernie Sanders supporters, right? You believe in shared poverty? Here. Sorry. You guys are like, nonsense. My precious Hillary has all the superdelegates she needs. So, anyway. always thought of Hillary Clinton as a president as like a hypothetical. Now it's a possible reality. It's like a really bad episode of Sliders or something. I don't know. Do you guys remember Sliders? No? Okay. It's just as well. I like to forget it too. So this is the alternating series test. And when I was in graduate school, I got a handout from another student who was teaching this, and on his handout he had like the list of tests, and under the alternating series test he had in parentheses wishful thinking test. I was like, wishful thinking test? What's that? And then I realized what he meant. Here, let me show you wishful thinking. Check this out. 1 plus 1/2 plus 1/3 plus ... right? In other words, that's the sum k equals 1 to infinity of 1 over k, right? Has a sub k equals to 1 over k. Clearly, that goes to 0 as k goes to infinity. Thus, a sub k converges. Therefore, convergent, right? But it's convergent. You deny that a sub k goes to 0? It does, right?
It only goes one way.
But you disagree that a sub k is convergent? You don't disagree with that?
Yeah.
See, you guys, you got to realize something. We're using the word convergent in two very different ways here, right? The convergence of a series refers to the convergence of the sequence of partial sums. I didn't say anything about the sequence of partial. I mean, this is false, okay? And this is what's known as wishful thinking. Just to be clear, no! Incorrect. Because what you need S sub n. You need the sequence of partial sums, right? Sum k equals 1 to n of 1 over k. You need this converges to get convergence of series, right? And some people feel so pedagogically strong about this that they won't even use the same word for the convergence of series. I follow the book. All right? And it's pretty standard terminology to say that the series converges or diverges. But you got to understand that there's a real danger for confusion here, right? I mean, this is not just some idle chit-chat I'm having here with you. This I have seen on the tragic third test of ever so many Calculus 3 students, or second test, or whenever this material came up. I mean, this is a very popular mistake, time-honored mistake. And it's also wishful thinking, right? Because it's so easy. You show it goes to 0, so you're done. Woo! No, you're not done. You have to show the nth partial sum converges. That's convergence, right? And in fact, the nth partial sum here, if you really calculate it, you can kind of calculate it from the integral test, at least to get an estimation on the nth partial sum. It involves the log. And the log does not converge. It blows up to infinity. And that's, I mean, as we worked out numerically that one day, it blows up rather slowly. Just like you said, it's the p equals 1 series. We know it diverges. In fact, today, I've already said it diverged about 2 or 3 times. I can say it another 12 times before the test, and there will still be some of you who tell me it converges on the test because a sub k goes to 0. You must free your mind of this confusion. I hope I have not just made that confusion part of your mind through this discussion. What's that? Exactly. How is that linked together? See, this, what does it say? If you have an alternating series with positive decreasing terms, b0, b1, b2, decreasing sequence of positive terms, then, here's the punchline, the series the alternating series, minus 1 to the k b sub k, converges, get this, if and only if b sub k goes to 0. In other words, with a little fine print, the fact that the terms in the series are going to 0 does suffice to prove convergence in the alternating case. So the wishful thinking isn't far from being true if you have some kind of nice alternation going on. But actually, okay, fine. I mean, actually, alternation of the series is like a huge condition. Actually, this story even plays out in like modern theoretical physics. There's places where the fact that you get this kind of plus-minus pattern from some exotic new symmetry suggests that we don't get new physics until much, much deeper physics is known. These kinds of masking theorems. It's one of the arguments for supersymmetry's existence. But now I'm getting off track. Do you have a question? Sorry, no talk of supersymmetry in here. Excuse me. So to prove this, 2 directions, right? Thankfully, not just one direction. So we wouldn't want that. Let's see here. So if I say that this converges if and only if b sub k goes to 0, that means I need to prove that if the alternating series converges, then b sub k goes to 0. And then conversely, if this goes to 0, then the series converges. Now, the first direction, which I had just illustrated in red, is really easy. Okay, so this direction, suppose the series, well, first of all, suppose that you have positive terms that are decreasing, okay? And then suppose the series converges. What does that mean? The kth term test tells us what? The kth term test tells us that a sub k, which is minus 1 to the k times b sub k here, goes to 0, right? Convergent series have the kth term going to 0. But what else do we know? If a sequence goes to 0, its absolute value also goes to 0, right? But the absolute value of a sub k is exactly b sub k. Thus, b sub k goes to 0. I think even if I was very sleepy, I could prove this direction. The other direction, it's a little bit sneakier. Let's go through it, though. So the other direction is what I've written in blue down here. All right. So in this direction, oh, wait a minute. What did I just do? Goodness gracious. So here's that part, right? Now, suppose b sub k goes to 0. The argument, what it does, the way to do this is to look at like an even partial sum. Let's analyze an even partial sum. So take n equals to 2j, all right? So think about that. You've got what? b naught minus b1 plus b2 minus b3, and then I just write the last 3. Minus b2j minus 2, plus b2j minus 2 minus p2j plus 1, right? And then finally plus b2j. Now, if you study this, each one of those things I've written green parentheses around, well, what can you say about it? How does b1 compared to b naught? Is it smaller or larger than b naught? What's that? Is b1 smaller? B1 is smaller, right? Because we said b is a decreasing sequence, right? So as we go on, they get smaller. So what we got here, every one of these green terms, green pairings, right? These are all positive. Do you see that? Positive, positive, positive. Just like we saw in this example over here, right? Positive, positive. Same pattern, right? the correspondence isn't precisely. I mean, there's a difference. That one starts at 1, whereas this one starts at 0. So don't try to be too precise in the comparison of these two things. But there's a shifting there of which terms are negative. But if we start at 0, then the even terms are positive in the series, and the odd terms are negative. And so there's always this. But on the other hand, the fact that it's decreasing means we're adding together positive things, right? So clearly, this whole thing is what? It's the sum of positive things, which is what? Positive, right. So we have that this is positive. We also have that this is s sub 2j minus 1 plus b sub 2j, right? That's just the definition of what is the relation between the 2j minus 1th partial sum and the 2jth partial sum, right? You take the one right before it and you add the next thing. That's the definition of like a finite sum. Anyway, my point is that that's positive, right? So you can look at two different things. You can look at the sequence, which is built from, let's say, the even terms, right? And you could look at the sequence built from the odd terms. If you look at the sequence built from the even terms, it's pretty clear. I mean, I could go another step here. Let's c sub j equals to 2j. I'm just saying define c sub j. What's that?
I think that term there should be b to the 2j minus 1. Plus 1 would be one step beyond 2j. So far as been going.
Oh, yeah. Sorry. Man, that earlier section, I tell you what. What am I going to do with them? Yes, that should definitely be minus 1. Thank you. As I have correctly over here. Right. Yeah. So you can see from this calculation that if you define, I mean, this is the definition right here, okay? If I let c sub j to be s sub 2j, right? If I define a new sequence, c sub j, to just be the even partial sums of this alternating series, it's pretty clear that that's a decreasing sequence, right? And what else? I mean, it's increasing sequence, rather. Did I say decreasing? I shouldn't say decreasing. It's increasing, right? Well, that's what I wrote here. It's increasing, right? You can see, I mean, I don't think I've quite proved that, but you could prove with like an extra like half a sentence that it's increasing. No, it's not going to 0. It's increasing, and it's Yeah, wait a second. Bless you. Uh-oh. I was about to talk myself into that I didn't need to split into even and odd sequences, so I know something's off in my thinking at the moment. Just a second here, guys. I somehow convinced myself that the even sums are decreasing. Is that even true? Well, I can't compare here because it starts at 1. Curses. Well, I think you can actually kind of see it here. Yeah. You can see it. If I draw this better, it's going to be the opposite story, right? But if I had fleshed out the details here better, you could see that in this example, The odd partial sums are doing what? They're going like that to the limit, right? The even partial sums are going like this, right? So if we play our cards right over there, we should be able to prove that either the even sequence is increasing or the even sequence is decreasing, and vice versa for the odd. I think the story is flipped over here because this one starts at 1. So in this one, the odd partial sums, the odd terms are positive, right? But the even terms are negative, and it's the other story over here. I think that turns it upside down. I do think we can argue that the even sums are decreasing. I want to say C sub j less than. And I don't want to say it goes to 0. That's nonsense. That's definitely wrong, and they should have called me on that. It's bounded below by 0 is my point because it's positive, right? I'm not saying 0 is the greatest lower bound. I did say it earlier today, but I obviously shouldn't say that. Gosh. C sub j goes to L, all right? Now, can we see that the even partial sum is decreasing? Funny. Well, anyway, tell you what I'm going to do for now. I will just summarize what we can show. You can show that S sub 2n decreases, whereas S sub 2n minus 1 increases. And it follows that S sub 2n converges to L, and S sub 2n minus 1 converges to L. And if both the odd terms and the even terms of a sequence both converge to the same thing, it follows then that the sequence converges to the same thing. I'm sorry, I seem to have butchered the proof of this today. I'll come back to it some other day. So I will give you your wish momentarily. We will go on to talk about homework, okay? Oh, one other thing. The alternating series estimation theorem states, and I probably should just come back to this other day when I finally fix this. If you look at the difference between the series and the nth partial sum of an alternating series, the error in that, the difference between the true sum of the series and this partial approximation to the series, is no larger than the next term that you haven't added. This is an amazingly simple theorem. To calculate the error in truncating an alternating series, just go one more step. That's true. That's what we're observing over here. The difference between sine of 1, which I'm claiming is actually the sum of this series, and 1. 1 is the first thing in the series. The error between the actual truth and this approximation just using 1, it's no larger than 1/6. And this is the numerical proof of that. Assuming calculators can calculate sine of 1 in radians correctly. Okay. And likewise, if I take sine of 1 minus 1 plus 1/6, in other words, if I use the first two terms in this alternating series, that is closer to sine of 1 than 1 over 120th. It is within 1/120th of sine of 1. This 5. In other words, 5/6 is within 1 over 120 of sine of 1. if I wanted to get within 1 over 720th of sine of 1, I could just do 1 minus 6 plus 120th. That would get me to within 1 over 7 factorial of sine of 1. And so it goes. That's the alternating series estimation theorem. It's nice, yeah. Okay, anyway, I shut up. I should come back and try to fix the multitude of errors I've made today. Probably do it tomorrow. Sorry, I was hoping to get to the more interesting stuff. Well, I'm going to erase. You guys okay? See, all right, anyway, let me start out with looking at section 12.3, I was asked to look at number 30 and number 32 by the earlier section. Let's look at I'll look at number 32 in section 12.3 to start with. So here we're asked to study the sum of 2 plus the cosine of k over the square root of k plus 1. Right, and the lower bound isn't given. I mean, you could make it 0. Well, yeah, you make it 0, I suppose, or 1, or whatever. So we're supposed to decide, does this converge or diverge, give some argument, right? So I think the way to do this one, my personal opinion, is I gravitate towards the fact that minus 1 is less than or equal to cosine k is less than or equal to 1. I always try to use that when I have a problem like this, right? That's the first thing I know. So what does that tell me? That tells me that 2 plus cosine k is what? Greater than or equal to what? Think of it in two. What's that? Greater than or equal to what? 1, right? Yeah. Yeah. But yeah, it has to be just what you said, smaller than 3 as well. Yeah. Or equal to it in principle. Although not in practice because k is an integer, right? No matter how many integers you look at, none of them are multiples of 2 pi, right? Okay, so what does that tell me? That tells me 2 plus the cosine of k over the square root of k plus 1, right, is what? Greater than or equal to 1 over square root of k plus 1. That's basically the p equals 1/2 series. Now, I mean, so, but the sum, 1 over the square root of k plus 1, diverges. By, well, that's the question, by what? I mean, how do you know that diverges? I guess technically that's not, what's that?
I should say what you want us to say. This diverges by this diverging by this here.
Yeah, I mean, we have to argue why is that divergent. I would guess for the moment, I would say by the following. Poor planning on my part. So how about this? If you look at the sum, I guess we need to pick a starting point, for example. I mean, I can think of about 3 different ways to show that diverges. Here's what I'm thinking. I can either use that's to help. I can use limit comparison. I could use integral test. Or I could use an index shifting argument. Any of the 3. Yeah.
I mean,
It depends whether I want to look for something smaller or larger depends on whether I think it converges or diverges. Yes, you have to have a gut feeling about what's going to happen here. My gut feeling about this is cosine k is nothing. It's just something that goes between plus or minus 1. It's irrelevant. And so this is essentially like 1 over the root, which is p equals to a half, which diverges. I'm trying to do that, but the thing is, this is not the p equals 1/2 series, is it? Right, but this is not the p equals a half series. I owe you an explanation. We are trying to be precise in here, yes? So let me look at, say, k equals to 1 to infinity. Here, I'll show you the most elementary way to show it. Well, this is the same as 1 over the square root of what? Square root, well, okay, I can write this. If I let this be j, right? Then if k is equal to 1, what does j start at? Two. Right. And if you just want me to be really pedantic about it, I know you don't. This is minus 1 plus the sum j equals 1 to infinity of 1 over the square root of j, right? But this diverges by the p equals 1/2 test. I mean, that's all we've proved is that 1 over k to the, or 1 over j to the p, if p is what? If p is less than or equal to 1, it diverges. If p is greater than 1, it converges. That's the p series result, not 1 over the square root of j plus 1. That wasn't what we had. But intuitively, it's the same thing, yeah. But intuition is dangerous if not checked by theorems, yes? Oh, all right, so there's number 32, right? This was 32, I think. And I'm not quite done yet, am I? So that diverges by the p equals 1/2 test. Therefore, the sum of 2 plus cosine k over the square root of k plus 1 diverges by the basic comparison test. Right. And just to be clear, using star and star star. I'll try to be precise here in how the logic is linked, okay? I still don't know how to do the one we got stuck on yesterday, by the way. That one over there. I mean, that's not in your homework, but still, it bothers me. What was your question? I could try. Now, do you have any kind of intuition? So here we're looking at k squared times 2 to the minus k cubed. Right? And it's a generic one. The lower limit's not given to us, right? All right, so what can we do here? What's that? Ah, very nice. That's so obvious. Why didn't I think of that? Integral of x squared 2 to the minus x cubed dx is equal to the integral of 2 to the minus u times du over 3. U equals to x cubed. So du is 3x squared dx, right? And so that is 1/3. 1/3 times the natural log of 2. There's a minus. Minus 1/3 natural log of 2, 2 to the minus u, plus a constant, if I remember right. If I differentiate that, chain rule brings down a minus 1. Derivative of that natural log, derivative of 2 with respect to u gives me natural log of 2 times 2 to the u. So the natural log 2's cancel. The 3 was there already. Yeah. And so cleaning this up, this is minus 1/3 natural log of 2. Thank you for telling me integral test. I was just about to go down a much darker path. So there's the antiderivative. Now, the question that I have is, does the integral test apply? What are the preconditions for the integral test? Yeah? Positive continuous decreasing on where? Yeah, we've got x squared times 2 to the minus x cubed is positive. Continuous. And is it clear it's decreasing? Not entirely yet to me. F prime of x is what, though? That's 2x times what? 2 to the minus x cubed. What? And then minus what? Minus 3 x to the what? Fourth, yeah? 2 to the minus x cubed. Don't forget your natural log of 2. And so if you rewrite this, what you got yourself is a 2x minus 3 ln of 2 times x to the fourth, all times 2 to the minus x cubed, right? It's fairly obvious that for x sufficiently large, that's decreased. That's negative, right? So in fact, it's all, I mean, okay, fine. The theorem is stated that you need it's continuous and decreasing on 1 to infinity. But, I mean, that's for the nicer aspects of the theorem. Truthfully, if I have that f is continuous, positive, and decreasing past some point, like 300, the integral test still applies, right? So I don't really care about where it starts being decreasing. The point is the derivative is definitely negative for large x. So I'm going to be a little bit sloppy here. So we can apply the integral test, and what does it give us? The integral from 1 to infinity of x squared 2 to the minus x cubed dx would be what? The limit as, say, t goes to infinity of the integral from 1 to t of x squared 2 to the minus x cubed dx. And then you just got to put that there, right? And let's see here. If you plug in 1, what does that give you? I guess it's just plus 1/6 ln of 2 if I haven't made a mistake. So then take the limit. Does it converge or diverge? Well, that much we can say. It does diverge or converge. Yes, that is true. What's that? No, this goes to Right, this goes to 0 because we're looking at 2 to a minus something huge, which goes to 0. And that's a constant. So the answer is 1 over 6 ln 2, which, by the way, is a constant, right? So the integral converges. Fine, be precise here. Therefore, by integral test, so much writing. Let's see here. Yeah, so what was this number? What did you say, number 30?
Yeah.
Number 30, yeah. Now, somebody asked me about number 14 in the earlier section. All right. So number 14 in the earlier section, number 12.3, number 14 was 1 over 1 plus 2 natural log of k. And I tried a few different things there. I tried to do the limit comparison to something relatively simple. It didn't turn out well. So you can ignore the limit comparison. Like limit comparison wasn't really helpful to me here. Let me erase that. So I mean, if you don't succeed, then you must dust yourself off and try again. You know, that's the way these things go here. So, but thankfully, a student earlier suggested that we should use the not limit comparison. Oh, no. For this one, I would suggest direct comparison, or use basic comparison. Against 1 over 2k. You can show. I mean, here, of course. You can show then, in fact, you can establish this inequality that 1 over 1 plus 2, the natural log of k, is greater than 1 over 2k. I personally don't find that immediately obvious. Maybe you do. I don't know. Here's a way you could argue that using calculus. If I want to show this, right, I want to show that 1 plus 2 ln of k is less than 2k, right? If I can show that, that gives me that this fraction is greater than that one, right? If this denominator is smaller than that denominator, that makes this fraction larger than that one, right? Oh, this goes back to that. So I want that. I trade this for a statement about functions. In other words, I want the function f of x to be positive, where f of x is built from 2x minus 2x, 2 log of x minus 1. So basically what I did was I traded this for 0 less than 2k minus 2 ln k minus 1, right? I personally love calculus. So then I changed this to a problem of calculus, which is I can analyze this function, 2x minus 2 log x minus 1, right? I calculate the derivative. F prime of x is 2 minus 2 over x. If I set that equal to 0, that gives me the critical points, right? Critical points are places where the function can change from decreasing to increasing, possibly, right? There's only one critical point. It's at 1. Okay? So what that tells me then is if x is greater than 1, the derivative is positive. In other words, this function's increasing past the number 1. So whatever the sign is of 2, f of 2, is also going to be the sign of k for any integer, any positive integer k, right? Right? And you can calculate f of 2 is positive. Consequently, f of 3 is positive, f of 4 is positive, f of 5 is positive, f of 6, you get the idea. Hence, the inequality I want is true, and so I'm off to the races, and I can use basic comparison to compare 1 plus